Hello everyone, my name is Maria Fernanda Flores-Rodriguez. I'm studying a bachelor in physics and I'm presenting a work titled Metal-Organic Frameworks and Graphitic Carbon Nitride Structures as Electrocatalyst for Hydrogen Evolution Reaction. We are facing an energetic dilemma worldwide. The World Energy Council in the World Energy Trilemma 2022 edition highlights that in order to stabilize the concentration of greenhouse effect gases in the atmosphere by 2050, we have to increase by 6 times hydrogen production. The growing demand on renewable energies has brought great attention to hydrogen as fuel because of its high energy density. Hydrogen is an energetic vector. It requires chemical processes in order to be obtained. Water electrolysis is a clean, efficient, and sustainable way of hydrogen production, consisting on the rupture of the water molecule into oxygen and hydrogen by oxygen evolution reaction and hydrogen evolution reaction respectively, using a suitable catalyst and determined current and voltage. Hydrogen evolution reaction, or HER, is a catalytic reaction based on the reduction of electrolytic protons to produce molecular hydrogen. However, the use of expensive noble metals as electrocatalysts for generating hydrogen from electrochemical reactions has limited the commercial production. Therefore, synthesis of low-cost electrocatalysts with high catalytic activity and good performance stability has become an important research topic. For this work, we tested 4 materials, 2 graphitic carbon nitrides and 2 metal-organic frameworks to evaluate their performance for hydrogen evolution reaction. Because of its porosity, these materials have abundant active sites, which may favor the reaction. The studied MOFs are zeolitic imidazolate structures like CIF8 and CIF67, based on zinc and cobalt respectively. The as-prepared CIF8 and CIF67 samples are carbonized at high temperatures to obtain porous conducting carbons. The graphitic carbon nitrides utilized are GC3N4 and GC3N5. For the electrochemical characterization, a 3-electrode system was used to carry out the electrochemical measurement of the as-prepared carbon materials in nitrogen-saturated 0.5 molar sulfuric acid electrolyte. For estimating the hydrogen evolution performance of each of the materials, linear sweep voltammetry was recorded in a selected negative potential window from 0 to minus 0.8 volt using a graphite electrode as counter-electrode and a saturated column electrode as reference electrode. The observed trend in overpotential is that black platinum is still the material that requires less overpotential in order to start the reaction, followed by carbonized CIF67 and CIF8, being the graphitic carbon nitrides in the last positions. The Tafel plots are graphed in a logarithmic scale using absolute value of the current density. The Tafel slopes obtained are 2.43 mV per decade for black platinum, 61.9 mV per decade for carbonized CIF67, and 153.75 mV per decade for CIF8. Results show that among the 4 studied materials, carbon derived from CIF67 requires relatively low overpotential and shows a promising Tafel slope, reflecting its highest electrocatalytic activity for HER. Perhaps the high porosity of the CIF-based carbon, along with abundant active sites, makes them suitable for HER. On the other hand, electrochemical activities of GC3N4 and GC3N5 are relatively low, and they could possibly be improved by preparing heterounions with carbonized CIF67 and carbonized CIF8. Thank you so very much for your kind attention.